Working? Okay, so good afternoon, everyone. Thank you very much for the invitation and the introduction. So as Antonin said, I'm going to talk to you about something quite applied, which is how to use optimization and somehow machine learning inverse problem to look at the brain at the high speed. So Antonin asked me to do a very applied talk, so I tried to do this, to stick to this. And the workshop is called Challenges, so I'll probably talk a lot more about the problems there are in this community than the actual solutions that I tend to develop myself, but I'll just give you some pointers on recent works. So, as I assume very few of you are familiar with what is brain imaging, I'll start from really basic so you understand what we're looking at, what it's useful for. So this is not an MRI scanner, this is what basic people have imagined what would be an MRI scanner probably a century or a couple of centuries before, where these types of devices are useful for seeing what people have in their minds. So reading people's brains. So what you more do these days with these types of devices is, for example, what you see here. So what you see here is your brain at rest. So you sit in a scanner for here 6 minutes, you close your eyes and you just think about nothing, and this is what your brain is doing. So this is functional MRI data, which is actually at a much higher rate than it actually is. What you see here is 6 minutes of data, and the frame rate is 0.5 hertz, which is meaning that you have one image every roughly 2 seconds. So this is very slow in practice. This is just accelerated for the rendering. So as you can guess, given the title of my talk, I'm not going to talk too much about fMRI, but I'm going to explain to you why fMRI is different from what is coming next. So fMRI, what's the principle, is that you have some neurons that are activated, and the neurons need some like fuel to support their consumption of energy, and this comes with your capillaries in your head. And you have hemoglobin that comes with oxygen, and when the neurons get activated, they use this oxygen, and at the end you have this hemoglobin which is deoxygenated. The thing is that depending on this oxygenation level, the scanner, the MRI scanner, can basically measure a contrast, meaning if there's oxygen or not, you'll feel the different signal. And the beauty of this is that you can then basically make images, and what I call bold signal images, and you can find contrast between what is activated and what is not activated. So what you see here is a typical brain activation map, where blue means it's lower than baseline and red is higher than baseline. So basically what fMRI measures is it going up or is it going down when the brain is doing this at this specific part of the brain. Right, so functional brain imaging, there are many different ways of doing this. I explained to you briefly fMRI, which is really, I would say, fine-grained spatially, but at a slow rate. What I want to talk to you about is EEG and MEG, which is more the types of research that I like to do. And what you see on this image, where you have here the temporal resolution and here the spatial resolution, when you do EEG, MEG, you have a very high sampling rate, and you will have data at a millisecond time scale. So you're going to get one time point, one measurement every millisecond. So what do you measure when you do these types of things? So you may have heard when you were younger or recently, if you had a chance, that when your neurons get activated, you have some electric charges that move inside the neurons. And when you move electric charges, this produces some tiny currents, and when these currents are big, you have Maxwell equations that tell you that you have an induction process. So these charges moving produce some electromagnetic field that you're going to be able to measure. How do you measure this? How do you make images from this? So what you see here on your left is kind of in between the first image I showed you and the really modern systems, which is the first EEG recordings. So what you see here is this poor guy that was this technician in the lab of the guy who came up with EEG a century ago, which is having electrodes on your head, and you measure differences of potential, okay, on the skin. So it's completely non-invasive, it's passive, you don't inject any currents, you just measure difference of potential. The other ways of sensing non-invasively these electric signals inside your brain is to use a technique called magnetoencephalography, or MEG, where now you're going to put some very sensitive device very close to the skin, something like 1 or 2 centimeters, and you're going to measure the magnetic field, which is extremely tiny, things that are on the order of 10 femtotesla. So like 1,000,000 times smaller than the Earth's magnetic field. And this is a modern system. I could have put the picture of the MEG system that you have very close to here at MRC, but since I'm French, I took a French picture. Okay, so in the end, how do you, I mean, it's a workshop about images, but in practice we collect these types of signals, and the signals allows you to make images. So the types of signals that we measure are typically like this, where here every line is a time series that corresponds to the measurement on one sensor. And you see the purpose of this figure is to show you basically what the raw data looks like, and also to show you that these types of data are pretty challenging because they are extremely noisy. So you see that you have slow drifts, you have eye blinks because the subject has to blink in the system for unacceptable reasons, but some people need to blink for when they stay still for multiple minutes. And you also have the heart of the people. When people are in the system, basically the heart does not stop beating, so the heart is basically corrupting the data. So we have this somehow messy input data, and we need to make science from it. Another example of artifacts where you see here every colored line that you see on this graph is basically types of artifacts that you need somehow to correct in order to do optimization. So this is really the dirty input part before you're allowed to do a variational problem and solve your optimization problem. But sometimes if you don't do this, basically whatever you can come up with fancy algorithm is completely useless for practical people. So here now I'm showing you data again, so you have a better sense of what's the input. I mean, most of you knows what's a natural image. I mean, you grew up looking at natural images. I guess very few people grew up by watching at these types of time series. So you wouldn't be able to tell me that this is clean data or not clean data, although probably you would tell me that this is not clean and this is clean. Hopefully, you would agree with me. Okay, so that's people, what they collect when they look at your brain active when people do cognitive neuroscience. So what's happening here is that before zero, the brain is not subject to any input stimulus, and then suddenly you ask the subject to do something, and you produce these types of brain waves that characterize what the brain is doing in this very indirect way through this propagation of the magnetic field. Okay, so basically based on this is quite a long introduction. And the problem is, now that you have this data, this non-invasive data outside of the head that are completely passive, how do you do imaging? How do you make images of the active brain? So first of all, you need to understand what are the equations that are driving the propagation. So you might have recognized this guy here. Okay, so this guy is Maxwell. He came up with these equations that basically drive the propagation of the electromagnetic fields. The interesting part for us is not that he has a fancy beard, but more that the PDEs here are linear, and in our case will not depend on time. Okay, so the reason it's not depending on time is not because there's no time derivative in Maxwell equations. It's because we are rather looking at something which are rather slowly varying over time, giving the distance from the source to the sensors. So we can use something that is called the quasi-static approximation, which means that in practice we have really linear PDEs that we need to solve in the medium of the head. So how do you solve this for the numerical people in the room? You're going to take this real MRI from the subject, you segment everything, and then you're going to assume that the blue thing has a certain electrical conductivity, the red thing is a different conductivity, the green is another conductivity, and then you're going to use boundary element methods. So some people use finite element methods to solve these types of things by doing some massive triangulations of the head. Most people in this community use these boundary element methods. So you solve these linear PDEs using this piecewise constant approximation of the medium. In practice, this linear PDEs means that you're going to have a linear forward problem that does not depend on time. Okay? So if you're a statistician, it means that you're going to have to solve a linear regression problem with a fixed design. Okay, so this is how the propagation works. And now I need to explain to you where is the signal coming from, and in the end what we hope to recover. So here this kind of like a potato that you see here is not a potato, it's actually a brain, a segmentation of the brain in which you blew, which means that you see inside the cell side, basically the folded patterns. So this is your brain, where here you have some activations, and in the end what you try to recover is this activity map, okay? Meaning that at every millisecond you're going to need to have a vector. We'll see that it's a vector of size p, where the p values, not the p dash values, but the p values in my vector are this basically the intensity of the activation at a specific location in the brain. And now if I look at this, what I call this matrix X, so X is going to be my unknown afterwards. One row of this matrix X is basically going to be the activation of one location over time, and if I take one column of this, it's just an activation map at a specific time point. Okay, so there are different ways of doing this, but the approach that basically I will advertise here, given the variational context, is to use what people call the distributed source model, where here you're going to discretize the brain. So for each of these yellow dots, you're going to compute the forward problem. So for each of these yellow dots, you integrate these Maxwell equations, and you compute what's going to be measured on all of these sensors. Okay. So solving this linear forward problem means obtaining a matrix that I call G, which G stands for the gain matrix, which is the jargon that people tend to use in this community, where here one column is just the sensitivity or the gain of a specific sensor for one specific location. Okay, so you can see this as the linear mixing matrix or the design matrix or the forward operator, depending on where you're coming from in terms of background. Okay, the game is therefore the following. I've got my data that I call here M, my measurements, where I've got N sensors, and I've got T time points, which are typically the 500 time points that I've shown you before with the real data. I've got this known mixing matrix that I derive from basically segmenting my MRI image, integrating my Maxwell equations, and the game is to recover X. And then what I can tell you is that typically you have a few hundreds of measurements, and you tend to sample the source space, or the brain, with something like 10,000 possible candidate locations. So in practice, this matrix is roughly between 100 and 300, and has something like 10,000 columns. Okay. The other thing which is important is this matrix is a dense matrix. Okay. So it is not an implicit operator that you may see in image processing. It's really a dense matrix that come up out of your boundary element method. And of course, you have some additive noise that is actually the noise coming from the sensors, but also coming from the rest of the brain that basically does not shut off completely when a specific brain region is involved in the task. So if you have a stats background, and just to maybe connect the dot with my notations, in practice you have this observation I call that a stats person would call y of t. So this is just a measurement at a specific time point. Here's a design matrix, and beta t is just the regression coefficient that in my case corresponds just to the amplitude of the brain activation at a specific location. Okay, and here again this design is dense, and here I've got my additive noise. So the game for me is to, in order to do science with these types of data, is to recover beta of t for an entire time interval. Okay, so again I'll show some how to solve this, but I'm going to focus a bit on the why this is a difficult math problem. So the first of all is that we have very poor signal models for this time series. Okay, we don't have a specific, we don't have Maxwell equations for these time series. Okay, or if we have equations for these time series, they are very low level, at the level of a few neurons. Here we measure things that are on the order of a few square millimeters of cortex. So we don't have any proper temporal model. And these time series are very diverse. You can have some very sharp transients, you can have some oscillations, you can model some stuff like a stochastic process. Some stuff are really deterministic shapes. And it's basically a soup of all this. And now if you look at the noise at the level of the sensors, if you look at the noise over time, you see that the noise is very strongly colored. What you see here in red is just the noise property. So this is the power spectrum density of the noise over the sensor. So if you have an additive white Gaussian white noise that we'll all like to assume, you would have a flat line. Here you have this kind of 1/f pattern. And here what you see in blue is just the same power spectrum density estimated when you put a brain inside the system. And basically everything that is between the red line and the blue line is basically what we are trying to understand. All this power, which is in between, is what is produced by the brain, and which is what you try to characterize, quantify, in order to better understand what the brain is doing with these types of device. Now this is just one sensor. Now if I look at just at the second order moments of my data, meaning I just compute the correlation of my data, this is how it looks like. So this is an actual covariance matrix estimated from the data when there's nobody in the system. So you see that the matrix is very far from a diagonal matrix. So the noise is clearly strongly correlated between sensors. You have some sensors that have a strong noise level and some sensors that have a poor noise level. In practice, if you want to do the best out of your data, you're going to have some MEG data, you're going to have some EEG data, and all these types of sensors have different noise levels and noise properties. We all know there's information in these types of measurements. In terms of stats and modeling, can we cope with all this? And something which is also quite uncommon for image processing people is the fact that we have a sensitivity of the device which depends on where you are in the brain. So here in this picture you see a source which is very superficial, very close to the sensor. And here I'm not really telling you what this picture quantifies, but here you see a small dot, which means that you have kind of a small uncertainty. So careful with uncertainty in terms of what I imply by this. But somehow you're going to be quite confident when you localize here. When you look at something which is more far away from the sensors, you're going to have some more uncertainty, quotes. What it means in terms of if you were to do deconvolution and image processing, I'm just telling you that every pixel of your camera has a different noise level, that the noise is correlated between pixels, and the blurring is depending on where you are in the camera. Okay? And this is my problem. Okay? It feels like anyway. Anyway, so why do people care about this problem even though there's so many issues and so many challenges? It's because these types of data are used across various applications in neuroscience that are both clinical applications or cognitive neuroscience applications. People use these types of devices to study sleep patterns, to study epilepsy. So typically with epilepsy you want to know where the signal coming from. So if you plan a surgery, you want to remove the right part of the brain. So you'd better not mess up your source localization because that would end up very badly. And people in cognitive neuroscience, they're trying to quantify where in the brain things happen. When is it happening first? What is the driving source of signal in the brain that propagates? All these questions is people that worry about the time resolution of the device and the measurements, and they need to use these types of modalities to study the brain. Right, so long introduction to come up with this variational formulation. Usually it's slide 3 in these seminars. Here it's slide 18. So in the end, the problem I want to solve looks like this. I've got my data, so assuming I've done some kind of black magic to assume that I've got a Gaussian additive white noise, I'm going to end up with the Frobenius norm here for the data fitting term, and I'm going to put a regularization. Here, remember, x is just my time series over all of my physical location in the brain. I'm not going to talk too much about the noise property and how to infer it from here, but there's some recent work we've been doing with a grad student where we try to do regression like this, sparse regression, when you have some heteroscedastic noise, meaning that you have a noise level which varies depending on all sensors. And you end up, and there are ways to have a convex formulation of this problem where you can also learn the noise property in a really principled way. Anyhow, for the rest of this talk, I assume that the noise is Gaussian IID, and I just have this standard Frobenius norm and my regularization. If I just use in my regularization a squared L2 norm, like most physicists would do, they just do a Tikhonov regularization because they want to minimize the energy in the sources, they're going to end up doing something like this. So here, these images show you just solving the Tikhonov regularization of this inverse problem. This is just resolved, so you don't see everything in red, but in practice, it's completely, you have a non-zero coefficient everywhere, and you see these patterns evolving over space and time. You also see in this video that you have a quite poor spatial resolution. Okay, you see some blobs which are basically 5 square centimeters, which is probably way bigger than the actual source in the brain. So if we look a bit closer, if I take my actual data and I use my Tikhonov regularization, and I look at specific locations that I know to be involved in the task, here are the time series that I try to I recover. What you see here is that this source, which is actually here, gets leaked into another location, even though it's 5 centimeters away. I say it's leaked because the correlation between these two time series is pretty much close to 1, even though the sources are quite far. So what it means is if you just use this squared L2 norm for your regularization, you have a really imperfect and crude deconvolution. Okay? You still have a lot of mixing and crosstalk between your sources and your estimates. And you also have this blurred estimate that you see in yellow, so you have a spatial resolution which is not great. So in practice, why most people still do this? Because it runs in something like 300 milliseconds. Computing this on actual data, once you have clean data, is really like this on any recent machine. And people like to interact quickly with their data. So for me, the game is to come up with something that fixes this issue, which is also running extremely fast. And this kind of a transition with optimization here. So this is the same data, but now I show you what a sparse estimate could give you, where you see here a much simpler picture, where you have 1, 2, 3, and 4 sources in the brain, which have 1, 2, 3, 4 time series of activation that capture exactly the same amount of variance in the input data. Okay, this is not underfitting. This is just using a different regularization to explain the same amount of data with something which is much simpler, because you only see the foci of activation at the specific brain locations. How do you use these sparse solvers then to make it fast? So remember, you have data over space and time. You have data over sensors, and you have data over time. You have a good model of the spatial propagation because you have Maxwell equations. You don't have any model for the temporal dynamics. So when you are like this, you use what you have. Typically, the things I have in my drawer when I do signal processing is short time Fourier transform, or short time, time resolved spectral estimation or representation, like here the short time Fourier transform. So just to explain to you, convince you that the model is actually capturing something meaningful with the data. Here, imagine you have this input data in blue. You do a short time Fourier transform. You only take the big coefficients in this 2D map, which is just the absolute value of the STFT. If you now invert the short time Fourier transform, you recover this time series that you see in red. And you see that by using just the very strong coefficients in this proper adapted representation, then you can denoise and have a very compact representation of your signal. This is extremely common in signal processing, but at least you see what it does on these types of data. So in practice, since you want to use this sparsity over on the time frequency domain, what I'm going to propose, and again, this is my approach to this. There are many different ways of doing it. But my approach to this is just to rewrite the problem, now writing x as just the synthesis of some complex value time frequency coefficients, time a wavelet, or short time Fourier transform operator. Okay? So now I'm going to reconstruct x directly by estimating the time frequency transform. And I'm not going to give too much details, but in the end, you just rewrite your optimization problem or rewrite your variational problem. Rather than minimizing over x, which are directly the time series, you're going to estimate the time frequency transform of all of your physical location in the brain. By doing this, you explode the dimension of your space, typically you multiply by 10 the number of unknown coefficients. But still, it works way better because you're suddenly in this representation, you're really, really sparse. And so just by blowing up the dimension, by increasing the sparsity with the right balance, then it works better. And a tiny detail also is that if you look at these types of signals, you can have things that are very transient and narrow in time, or rather long. So the way we do this, we use a set of blocks of dictionaries at different resolution, which is also quite common and proposed in image processing, like the morphological approach for deconvolution. Okay, so what types of regularization do I use to do these types of things? Typically, you want to be sparse over space and you want to be sparse over time. So what I'm using is what people call in machine learning a sparse group lasso, which is just a group lasso which allows you to select brain regions and then to be sparse within the brain, for each brain region, be sparse in the time frequency domain. And one way to do this is to frame the problem like this. And the benefit for me by doing this and not coming up with something different is that this regularization is completely separable in terms of location in the brain. It's separable in the location in the brain, which means that I'm going to be able to use very fast solvers based on block coordinate descent. I'm going to loop over each block of coefficients, which is going to correspond to every row of my matrix Z, so every location in the brain. And I'm going to update the coefficients in my regression problem, in my inverse problem, by sequentially updating each of the coefficients in a block coordinate descent manner. I'll come back to this in a minute before concluding. So this is now what you see, and in terms of interpretation of these types of data, suddenly you see a very clean picture about where things happen in the brain, where they start, and when things emerge. And you can see something that is extremely hard to see otherwise, which is when you activate here and then you propagate here. So for the brain imaging people, people here interested in brain imaging on neuroscience, this corresponds to a task where you put an electrical shock on the wrist of your subject on the left hand, and this electrical shock produces an activation on the right somatosensory cortex, and then this propagates here. So you see it starts at 50 milliseconds. So here it takes something like 20 milliseconds for the first response to appear in the primary somatosensory cortex. Then at 50 milliseconds it goes here, and then 20 milliseconds before it goes on the opposite side, and then there's something that comes up very much later. Okay, so you really see this sequence of activations by using these types of sparse approaches. In terms of optimization, I focused on the challenges, but I'll still say a few words about how to use the best of what we can do in optimization to solve these types of problems. The way we solve this is using block coordinate descent. I use a penalty which is separable, which means that I'm going to be able to use result from Tseng, where I'm going to loop over coordinates and minimize like this. We use these types of algorithms for these types of design because this is dense. This is also what people use in machine learning. People who know things like strong rules or GLMNet packages in R, they're exactly using the same of techniques, and they're really state-of-the-art for these types of sparse problems. The thing you can also use is what people call screening rules or working set strategies. The ideas of these strong rules, screening rules or working set strategy is to use convex results like duality in order to know if some of the constraints can be ignored, which means that in the dual, some of the brain region can be completely removed from the optimization. So can you remove, for me, parts of the brain, so I only have to focus in the relevant part which explains my data. And in terms of, this is not much information, but this is basically illustrated with this algorithm. So this is, you don't have time to pause this. The only thing that is interesting here is when you do this block coordinate descent, you're going to update every coefficient sequentially, or block of coefficients sequentially. But if you use these screening rules or these working set strategies, sometimes you don't have to do anything. You know that this coefficient will be 0, and you have to ignore it. And when you have a dense design for which computing a dot product with just one column of the design is extremely cheap, typically don't do this with the Fourier transform or wavelet stuff. But if you have a dense design, you can do very quickly these dot products, And it's really hard to beat these types of coordinate descent methods. And in practice, of course, since you remove a lot of computation, you can save a lot of time. All right, so I'm going to conclude real quick. So take-home messages, which are more coming back to the challenges that I pointed to. So we have very weak signals and extremely noisy. The noise is very complex because it comes most of the time from the brain, which has, by nature, very non-stationary and complex statistics. We want stuff that work with data more and more. So on purpose, I said that data which are not so small. I try to avoid the big data term in my conclusion. But people now these days do population images. They work with 100 subjects, which are roughly 10 gigabytes per subject. And you want something that works out of the box. If the bottleneck is the subject or the clinician or the neuroscientist looking at data, people start to have problems because, as you all know, grant money is a scarce resource. And if you spend all your money paying undergrads or grad students looking at clinic data, then it's probably not a very good use of their time. And maybe one of the take-home message of my slides, I'm sorry for people who have seen this before, but I do a lot of software and open source tools because I think, I see myself as a middleman in this community. I'm between the physicist and I'm between the neuroscientists. I try to do algorithms, so the physicist gives me data and I give software to the neuroscientists that have no idea what a block coordinate descent algorithm is. All they want is a software that they can use and makes figures that they can publish. So in order to do this, what the things I do when I have time, which is becoming less and less time these days, I write these types of software like scikit-learn, that is a toolbox to do machine learning. A lot of the sparse solvers in this scikit-learn are coming from the same types of lines of research. And in the context of brain imaging, I write this software called M&E, which is used at MRC, where I will go tomorrow, where people use these types of software to analyze their data, and that makes a difference and impact. We've heard impact before, but I guess this contributes to this. It's a really open project, so there's a lot of investment that is spent on building a community of people around open source software. It's a lot more than just putting stuff on your web page. I spend probably more time educating people than writing code myself these days. But I guess I'm just getting old. And I think that's it. So if you have any questions, please let me know or come to the coffee break. Thank you very much. Yes.
You showed about the noise characteristics when you talked about obtaining the noise in an empty instrument.
Yes.
So for MEG, that's clearly you get random fields from the earth. But for the electric field, you would need to have some.
For the electric fields, indeed, you cannot record without a subject in the system because the electrodes. So typically, you assume that before the simulation, this is what you get as noise, and either you take this for granted or you estimate jointly the noise after post-stimulation, assuming that the signal arises after. And you can pose the problem this way, where you use before stim data, assuming this is just noise, even though this is probably a lot more brain than measurement noise.
And also just to follow up, because you're using a combined forward model for MEG and EG, they have completely different physical units, so there must be some scaling of the operator.
Yeah, so typically when you estimate the noise levels, you need to scale the operator. So this is a very good question. In practice, if you want to, either you know the noise level before and you just whiten the data and then basically somehow put everything back in the same scale, or you need to kind of standardize by block and then you can write your problem in a complex way by optimizing over noise and coefficients. But this is clearly a very relevant problem, challenge. Yes?
So you are producing this huge matrix which has 10,000 to a few hundred. this is like your calibration thing. It's done once and for all. Yeah. For all cases.
So no, for every data, we're going to have to re-estimate this X matrix, which is, I mean, the 10,000 by time is really the data. Or unless you speak about the design,
No, the design. When
the design is subject specific. So for every subject in the scanner, we put them in the MRI, we run software for 8 hours, we segment the head, we have all the triangulations, we put this into a BEM solver, and we get this individual, like subject specific for our model.
So every subject has a huge
Yes.
calibration matrix
Yes.
in it, and then you have a sparse superposition of signals.
Yes.
You are in the sparsity model.
Yes, for the source, for the X, I'm going to assume that the source is coming from a few brain regions, and these brain regions are sparse in the time frequency domain, as I showed you.
So when you have when the sparsity obeys a certain condition with respect to this matrix, you can use linear programming or something like this.
So with the so with
L1, the L1
yeah.
giving you the
So if I just had an L1, I could use just an LP to solve it. But here we have these group structures, and also this in practice the groups are not are overlapping. So we have a kind of overlapping group problem. So we use proximal algorithms. I did not go into details, but you have closed form solution for the procs of these types of hierarchical group lasso style priors. You can also write explicitly the dual problem. So you can use active sets. I had absolutely no time to go into detail of this.
Okay, so thank you. Very interesting.